On a table in a small observatory room in Arizona in January of 1930, two glass plates lay side by side beneath a low lamp. Each plate held an image of the same patch of sky, taken 6 nights apart. Against the blackness of both images, thousands of points of light sat perfectly still, stars too distant to move, locked in their positions by the sheer enormity of the space between them and this room. But on one plate, in one small corner, among all those thousands of frozen lights, a single point had shifted. Not by much, a fraction of a millimeter. The width of a human hair would have dwarfed it. And yet the shift was there, deliberate and real, a slow step sideways across 6 nights of sky. The man who noticed it was 24 years old. His name was Clyde Tombaugh, and he had been hired to do exactly this work, to sit at a machine called a blink comparator and cycle between two photographic plates of the same star field, watching for anything that moved. The blink comparator switched rapidly from one image to the other so that fixed stars appeared to flicker in place, their positions unchanged between exposures. Anything that had moved during the interval between photographs would appear to jump, a small deliberate step against the stillness of everything else. For months, Tombaugh had been doing this work. Hundreds of plates, hundreds of thousands of star points. And then, on the 18th of February, 1930, that fraction of a millimeter declared itself. The dot of light he had found was real. It moved at the pace of something genuinely distant, slower than a nearby asteroid, slower than any of the inner planets would have appeared to move across those plates, but moving nonetheless with a measured, unhurried drift that placed it far out in the solar system, beyond the orbit of Neptune. It was given a name within weeks of the announcement, suggested by an 11-year-old girl in Oxford who had been thinking about the Roman god of the underworld, Pluto. The name suited something found in darkness at the edge of the known world, and it stayed. The discovery had been expected, in a way, not Pluto specifically, but something. For decades before Tombaugh sat down at his blink comparator, astronomers had suspected that the orbits of Uranus and Neptune were being pulled very slightly off course by the gravitational tug of an unseen body further out. The astronomer Percival Lowell, who had founded the observatory in Flagstaff where Tombaugh would eventually work, had dedicated years of his life to hunting this hypothetical body. He called it Planet X. His calculations predicted a large, massive world lurking past Neptune, something substantial enough to leave a gravitational signature on its planetary neighbors. Lowell died in 1916 without finding it. The search continued after his death, halted by legal disputes, then resumed. And it was that resumed search that eventually brought Clyde Tombaugh to Arizona, and to those photographic plates, and to that fraction of a millimeter shift that changed what the solar system was understood to contain. There was a complication, though it took decades for its full weight to become clear. Pluto, as measured in the years after its discovery, was too small to account for Planet X, too small by a considerable margin. The gravitational pull that Lowell had predicted required a body with real mass, a Neptune-like giant, something hundreds of times heavier than what Tombaugh had found. As instruments improved and the mass of Pluto was measured with growing precision, it shrank, not literally, but in the estimates. What had seemed possible to be Earth-sized or larger gradually resolved to something much smaller, until eventually the full picture emerged. Pluto was smaller than Earth's moon. It weighed less than a fifth of what the moon weighs. It was nowhere near massive enough to perturb Neptune's orbit in any measurable way. The perturbations Lowell had based his predictions on turned out to be artifacts, measurement errors in the original data, Slight inaccuracies in how the positions of Uranus and Neptune had been recorded across decades of observation had introduced a ghost signal into the calculations, a wobble that was not really there, pointing toward a body that did not exist in the form he had imagined. Pluto had been found not because Lowell's prediction was accurate, but because Toombaugh had been thorough. He had looked at enough sky with enough care that he had found something real, something genuinely there, even if it was not the thing the search had been designed to find. That is sometimes how discovery works. The answer turns out to be a different shape than the question. For 76 years after its discovery, Pluto was the ninth planet. It appeared on charts and in textbooks and on the walls of schoolrooms. Children memorized its position at the edge of the planetary sequence. It was small, yes, and cold, and its orbit was strangely tilted relative to the plane of the other planets, and it crossed inside Neptune's orbit for part of each long year. But it was a planet, and that was settled. The settlement lasted as long as Pluto appeared to be alone out there, the single small body at the solar system's edge, orbiting in a region otherwise thought to be mostly empty. The region was not empty. Beginning in the early 1990s, astronomers using powerful telescopes at observatories in Hawaii began finding other objects in the same broad orbital territory as Pluto, small icy bodies orbiting the Sun far beyond Neptune, following paths that placed them in the same dim outer disk of the solar system where Pluto had always been. By the early 2000s, dozens had been found, then hundreds. The picture that emerged was not of Pluto as a solitary outpost, but of Pluto as one member of an enormous community, the largest known member, at that time, of a vast population of icy bodies that crowded the outer solar system in numbers no one had suspected when Toombaugh had first blinked his plates. And then, in 2005, that picture changed again. 3 astronomers working at Palomar Observatory in California, Mike Brown, Chad Trujillo, and David Rabinowitz, discovered a new object in the outer solar system. They found it in archived images, a faint point of light sitting far beyond Pluto's orbit, moving slowly and deliberately through the same outer darkness where Pluto moved. When they measured it, the object appeared to be at least as large as Pluto, possibly larger, and Borthaifarting. Its orbit was extreme, carrying it out to nearly 97 times the Earth's distance from the Sun at its farthest point, a distance so great that light takes more than 13 hours to cross it. The new body was eventually named Eris, after the Greek goddess of strife and discord. The name was fitting. Its discovery did not resolve the question of what the outer solar system contained. It opened the question wider and pressed it into territory the astronomical community could no longer defer. If Eris was as large as Pluto, or larger, and if hundreds of other bodies occupied the same orbital region, then the category of planet faced a genuine problem. Either the solar system had 10 planets, or 11, or some number that might grow with each new discovery, as larger and larger objects were pulled from the outer dark, or the boundary of what counted as a planet needed to be examined more carefully than it had been in the decades when Pluto stood alone, and the definition did not particularly matter. The examination happened in Prague in August of 2006 at a meeting of the International Astronomical Union. Astronomers from around the world had gathered, as they do every few years, to conduct the business of their science, to agree on naming conventions, to ratify standards, to do the careful bureaucratic work that holds an international scientific discipline together across languages and institutions and traditions. Among the items on the agenda was a definition of the word planet. It had never been formally defined. For as long as astronomy had been a science, the category had been understood intuitively. A planet was one of those bodies. Everyone knew what was meant, but Eris had made everyone know that this was not enough any longer. The definition that emerged from Prague required three things. A planet must orbit the sun. It must be massive enough that gravity has pulled it into a roughly spherical shape, a condition called hydrostatic equilibrium, in which the body is large enough that its own weight compresses it into a ball, rather than leaving it in whatever irregular form the rock or ice originally took. And it must have gravitationally cleared the neighborhood of its orbit, sweeping up or scattering away the other smaller bodies that share its orbital path until it is the dominant gravitational presence in that region of space. Pluto met the first two requirements easily. It orbited the sun. It was spherical. But the third requirement was a different matter. Pluto's orbit was shared, not cleared. The same broad orbital territory was home to thousands of other icy bodies, many following paths similar to Pluto's own, and Pluto had not cleared them. It was not massive enough to have done so. In this respect, in the specific matter of gravitational dominance over its neighborhood, Pluto had never been what the other 8 planets were. It was a member of a population, not a solitary sovereign of a region of space. The vote among the assembled astronomers was 424 in favor of the new definition. Pluto became a dwarf planet, a category that included Eris and would eventually include other large outer solar system bodies as well. The room in Prague was not loud when it happened. There was no particular drama in the moment itself, a show of hands among a few hundred scientists in an afternoon session of a professional conference. The drama came afterward and outside in the response of people who had grown up with Pluto as a planet and felt something quiet shift when it was reclassified. Some of that feeling was sentimental, and people knew it was sentimental and felt it anyway. Pluto had been there for 76 years. At the end of the list, a small cold world with a name from myth, and something that had seemed fixed had been changed by a room full of experts with a show of hands. Not all of those experts agreed. Alan Stern, who had spent years working on a spacecraft mission to Pluto and knew its character more intimately than almost anyone alive, publicly rejected the cleared neighborhood criterion. His argument was specific and testable. The same standard, applied rigorously, would remove Earth, Mars, and Neptune from the list of planets if those bodies were relocated to the outer solar system, where the orbital neighborhoods are so vast that no planetary mass could be expected to fully dominate them by the criterion's own measure. The definition, in Stern's view, was not a physical description of a natural category. It was a line drawn in a place that happened to separate the 8 familiar planets from everything beyond them, and the placement of the line was doing work the underlying science did not entirely support. The disagreement has not been resolved. It is an open question in planetary science, not whether the facts about Pluto are correct, but whether the category those facts assign it to is the most useful or accurate way to understand what kind of body it is. Some researchers continued to use the word planet in informal and technical contexts for Pluto and bodies like it, arguing that any world massive enough to achieve hydrostatic equilibrium has a geophysically planetary character, regardless of what surrounds it in its orbital neighborhood. Others found the IAU definition practical and well-bounded, a reasonable way to keep the category manageable as new discoveries multiplied. The science of naming is not the same as the science of knowing, and both continued alongside each other. Eris, at the center of all this, sat in the cold dark at the edge of its long looping orbit, unchanged. It had been there for the full history of the solar system, approximately 4.5 billion years. tracing an ellipse so elongated that its closest approach to the Sun is inside Pluto's orbital range, and its farthest is nearly 100 times the Earth's distance from the Sun. At that far end of its path, where it spends most of its time, it moves almost imperceptibly slowly, a pale frost-covered sphere in a sky where the sun is just the brightest point of light among thousands of others, its warmth a whisper rather than a presence. The light leaving Eris's surface at that distance takes over 13 hours to reach any telescope pointed at it from Earth. What arrives is old light, already ancient by the time it crosses the gap, carrying information about a surface that has changed very little since the solar system was young. Pluto's orbit, by comparison, is almost neighborly. It lies between 30 and 50 times the Earth's distance from the Sun at its most distant, and crosses inside Neptune's orbit at its closest approach. By the standards of the outer solar system, this is practically nearby, but even so, the Sun seen from Pluto's surface would provide roughly 1,000 times less warmth than it provides at Earth. A brilliant star in a black sky, giving light without real heat, illuminating a surface whose temperatures fall to around negative 230 degrees Celsius. The year is long. Pluto takes 248 Earth years to complete one orbit of the Sun. The month Tumba found it. In the cold of an Arizona winter in 1930, Pluto was at a particular position in its enormous ellipse. By the time of the vote in Prague in 2006, it had moved less than a third of the way around its path from where it had been discovered. It had not completed a single orbit of the Sun since human beings first knew it existed. The orbit continued, as it always had, a slow tilted ellipse, carrying a small round world through the same outer territory it has always occupied, through the same population of icy companions it has always shared that territory with. The vote in Prague did not alter the ellipse. It did not change the size of Pluto, or the composition of its surface, or the length of its year. It changed a label in a database, and a line in a textbook, and the number a child memorized when reciting the planets in order from the Sun. The body at the end of that orbit went on completing its long circuit on the same unhurried schedule it had maintained since the earliest centuries of the solar system, before there were eyes anywhere in this solar system to see it, before there was a word in any language for what it was. What it was had always been there to find. The glass plates and flagstaff, the blink comparator, the 24-year-old looking carefully at a fraction of a millimeter of shifted light, all of that came later, long after the object itself was already old. The solar system has always contained more than the bright, warm inner planets. It has always extended outward into a vast, cold, crowded outer region where small icy worlds follow their long orbits in a darkness that is not emptiness. The name Pluto attached to one of those worlds. The name dwarf planet attached to the category. The names came and were debated and were sometimes changed, and the world they referred to continued its orbit in the quiet of the outer dark at the same steady pace it has always held, on a path no vote has ever altered, carrying its round cold mass around the Sun in the long, slow, patient way it has done for longer than there has been life on Earth. To note the passage of such time, the motion of a small world in the outer solar system requires no permission and no consensus. It does not wait for the meeting to adjourn or for the final tally to be confirmed. It does not know what a planet is, or what a dwarf planet is, or why the distinction might matter to the warm, brief creatures on the third body inward from the Sun, who argued about it one August afternoon in a conference room in Prague. It only continues, a faint, cold, round mass in an ellipse the same ellipse it has held for billions of years, carrying whatever name has been given to it through the deep dark of the outer solar system, patient and silent and entirely indifferent to the precision of the categories it inhabits. The light from Pluto, such as it is, makes a long crossing before it arrives anywhere. Out there at its orbital distance, the sun has diminished to something that gives a pale, directionless illumination, washing faintly over a surface of ice and rock, bouncing back outward into the void, and then traveling for hours, 4.5 to 5 hours, depending on the geometry of the moment, before it reaches the first telescope in the inner solar system that might record it. What arrives is not a view of the world as it is now, but as it was when the light left, which by the time any image is formed has already shifted again in its long orbit, rounding its ellipse by another small, unhurried increment. The world and its image are always slightly out of step. That slight gap is simply what distance means, and yet the distance is not nothing. Clyde Tombaugh, at 24, sat down at a machine and looked carefully at a field of thousands of stars and found the one point of light that had moved. That was a kind of knowing, precise, patient, earned through hours of careful attention to plates that could easily have been dismissed, to a shift so small that a less practiced eye might have filed it away with the noise. He had found something real in a dark field, and the name Pluto had followed from that finding, and the spacecraft that would eventually be built to travel there would bear that finding's number, built to visit the world. Tombaugh found in a fraction of a millimeter of shifted light on a cold winter morning in an Arizona observatory room, nearly a century before anyone alive today was paying attention to the sky. A glass plate is a record. Light touched a chemical surface and left a mark, and that mark was still there 6 decades later, when the scientists who built a spacecraft mission needed to know the precise position of the world their craft would visit. The plates Tombaugh worked with still exist. The comparator still exists. The light that passed through the lens and onto the emulsion in January and February of 1930 made a permanent impression in a way that the light itself, having crossed the observatory and met the glass, did not survive to report. What lasted was the trace, the mark, the fraction of a millimeter of difference between one plate and another that meant a world had been found in the outer solar system, and that the solar system was larger and stranger and more populated than anyone had been quite sure it was before. The debate about what to call that world will go on. Reasonable people with real scientific knowledge and careful arguments disagree about where the line should be drawn and whether drawing it the way the IAU drew it serves the science best. That kind of disagreement is how a scientific field handles questions that sit at the edge of its categories, not with silence, but with ongoing argument, with new data, with revisions that sometimes come decades apart. The outer solar system continues to yield new objects. The census of what is out there grows slowly with each passing year. Each wide field survey, each archived image blinked against another archived image from the same field 6 nights later. There is still much out there that has not been found, and the finding is still done, in essence the way Tombaugh did it, by looking carefully at a field of lights and noticing the one that moved. Pluto is where it has always been. Its orbital path carries it through the same deep outer dark it occupied before the observatory in Flagstaff existed, before Arizona was a state, before anyone on this planet was speaking any language in which the word planet yet existed. The ellipse is the ellipse, slow, tilted 248 years from one point back to the same point, the world inside that ellipse, going around and around in the patient, indifferent way of all orbital motion, which does not hurry and does not slow and does not require that anything down here agree on what name best describes it. The lamp above the two glass plates and flagstaff burned for a moment and then went out. The plates were filed away. The blink comparator stood in its room through years and decades. Outside, the sky continued. In the outer solar system, in a region colder and darker and more densely populated than anyone in that room in 1930 understood, a small round world completed another small arc of its enormous orbit, one more step of its slow passage around the sun, unchanged and unhurried, as it had been moving before the discovery, and as it would go on moving long after the last disagreement about its name had settled into the quiet of accepted history and been filed away like a plate in a drawer, in a room in the dark, under a sky full of points of light, only a few of which have moved. At a distance of more than 4.5 billion kilometers from the sun, the light that reaches you is not the light you know. It arrives diluted to a fraction of what falls on Earth. Not the warm gold of a summer afternoon, not the pale silver of winter morning, but something quieter than either, a steady, faint illumination that would not be enough to read by, yet still enough to cast a shadow. The sun, seen from this place, would fit behind the width of a pencil held at arm's length. It shines. It is still the brightest object in the sky by an enormous distance, but it gives no warmth a human body could detect, and the darkness around it is absolute, a black so complete and so permanent that it has no edges, only depth. This is the neighborhood New Horizons was sent to find. The spacecraft left Earth in January 2006, moving faster at the moment of its launch than almost any object humans had ever built. Its speed at that moment was close to 58,000 kilometers per hour, fast enough to cross the continental United States in a few minutes, fast enough to reach the moon in roughly 9 hours. And it was not enough. At that speed, the journey would still take nearly a decade. The outer solar system does not reward impatience. It rewards commitment and long calculation and the willingness to build something careful and send it away into a silence from which it will not return. The spacecraft was small, roughly the size and shape of a grand piano, and considerably lighter. It carried 7 scientific instruments and enough electrical power from its onboard nuclear source to run a pair of ordinary household light bulbs. It was not built for comfort or redundancy or the slow accumulation of data over years of orbital looping. It was built for one long, fast pass, a single encounter at closest approach, during which all its instruments would be open and working and pointed, and after which the geometry of the encounter would carry it onward and past, still accelerating gently, still bound outward into the dark beyond any world yet named. For much of the journey, it slept. Not all of it, not continuously. Periodic checks kept its systems awake and communicating, but for long stretches, the instruments were powered down, the data processors were resting, and the spacecraft moved in something close to hibernation, its antenna pointed loosely toward a sun that had become, from its perspective, merely the brightest star in a sky full of stars. The people who built it went about their lives. Years passed. The spacecraft moved through the gap between planets, with nothing to mark its passage. No landmarks, no atmosphere, no friction, only the imperceptible tug of solar gravity decelerating it by the smallest possible amounts across the longest possible distances. In February 2007, 13 months after launch, the spacecraft reached Jupiter. What happened there was not a detour. It was a maneuver planned with precision years before liftoff, the spacecraft threading a path through Jupiter's gravitational field in a geometry calculated to extract energy from the planet's own motion around the Sun. Jupiter did not slow down. Its mass is too vast for any human object to measurably affect. But the spacecraft, swinging close and then away along a carefully chosen arc, emerged from the encounter moving approximately 4 additional kilometers per second, faster than it had arrived. That additional speed, held and sustained across the following years, shaved roughly 3 years from the journey. The spacecraft used Jupiter as a step, a way of trading the giant planet's orbital momentum for the smaller craft's velocity, and then it continued outward, faster now, into the long dark between the outer planets. There are no milestones in that dark. Distance accumulates without ceremony, marked only in the telemetry that the spacecraft sent back to Earth and the calculations that engineers ran against it to confirm it was still on course. The signal traveled from the spacecraft at the speed of light, and even at that speed, it took hours to arrive. A message sent from Earth would take hours to reach the spacecraft, and hours more for any reply to return, meaning that by the time a problem was known, it was already old, and any correction sent in response would not arrive until the problem had already resolved itself or grown beyond the reach of correction. The team on Earth learned to plan for contingency, to build decisions into the spacecraft's own programming, rather than relay them in real time, to trust a machine across a gap that conversation could not bridge. Across the years after Jupiter, the images of Pluto taken by the spacecraft's cameras began to change. At first, they showed almost nothing, a pixel or two of brightness against a dark field, the resolution too coarse to distinguish shape from noise. Then slowly, as the distance closed, the pixel resolved into a point, and the point into a smear, and the smear into something with structure. In the final weeks of approach, the images began to reveal a shape that no one had predicted with confidence. There was a brightness on one face of the approaching body, a rough, large, pale region that caught the eye even in the low-resolution images of approach. It was not uniform, it had a shape. The shape was, by general consensus among the scientists monitoring each new downlink, a heart. The formation visible in those approach images, and in the close encounter images that followed, covered an area roughly the size of Texas and Oklahoma combined. It was a basin, a broad low depression on Pluto's surface, and what filled it was ice, not water ice, but nitrogen ice, carbon monoxide ice, and traces of methane ice, compressed and layered across the floor of a structure that had formed and been filled over timescales too long to step through comfortably. The western half of this feature, the left lobe of the heart shape when viewed from a particular orientation, became the focus of some of the closest attention among the scientists studying the return data. It was named for the Russian word for calm sea, and it was named well. The surface there was smooth, not roughly smooth, the way a frozen pond is smooth after a cold night, but smooth at scales that implied active geological renewal. No craters older than 100 million years or so, very few craters at all, a surface that had been resurfaced recently enough, in geological terms, to have erased the record of earlier impacts. This basin takes the name Sputnik Planitia. It stretches approximately 1,000 kilometers from one side to the other, and across its floor the ice is divided into rough polygonal shapes, each of them hundreds of kilometers wide, each of them bounded by shallow troughs where the surface material has subsided between the rising cells. The cells are not frozen in place, they move. The mechanism that drives this motion is the same mechanism that drives a lava lamp. Heat applied from below causes the material at the bottom to become less dense than the material above, and it rises slowly, spreads at the surface, cools, becomes denser, and sinks again at the margins. The time scale of this overturning in Sputnik Planitia's nitrogen ice runs not in minutes but in hundreds of thousands of years. Each slow rise and fall of a convective cell is a geological event, a shift in the distribution of material across the basin's floor, and the pattern of polygons visible in New Horizons images is the still image of a process that has been operating, unhurried and continuous, for longer than human civilization has existed. The heat that drives this convection comes from within Pluto. Not much heat. Pluto is a small body, and whatever radioactive elements were present when it formed have been slowly decaying across 4 billion years, their warmth diminishing across that span. But a small amount of internal heat is enough to keep the nitrogen ice at the floor of a deep basin cycling, slowly and perpetually, long after the surface has cooled to temperatures at which nitrogen would ordinarily remain perfectly still. Along the southwestern edge of Sputnik Planitia, where the bright basin meets a darker, more varied terrain, the surface rises abruptly into mountains. They are not hills or ridges. They are mountains in the full sense, tall, steep, and structurally coherent, their peaks reaching up to approximately 3,500 meters above the surrounding plain, which is comparable in height to the taller peaks of the Rocky Mountains. What makes them strange is what they are made of. The temperature on Pluto's surface at the time New Horizons passed was approximately 230 degrees below 0 Celsius. At that temperature, nitrogen ice and methane ice are not structural materials. They are as soft as fresh snow. They cannot hold up a mountain, but water ice at those same temperatures is as hard as rock, harder in some ways since it does not creep under its own weight, the way warm rock does at the temperatures found in Earth's crust. The mountains along the edge of the bright basin are built from water ice. They stand because water, which on Earth flows in rivers and falls as rain, exists here as the rigid, unyielding bedrock of a world. The names given to these ranges carry the tradition of naming features on Pluto after explorers and discoverers of the unknown. The Hillary Montes honor Edmund Hillary, who climbed Earth's highest peak. The Tenzing Montes honor Tenzing Norgay, who climbed it with him. On a world at the edge of the solar system, their names rest on mountains of frozen water that have never been touched and will not be touched for any foreseeable span of human history. Above the surface, above the mountains, and the bright plain and the darker regions that spread beyond them, the atmosphere of Pluto extends into a column of haze that New Horizons measured with an instrument, pointed back toward the sun after closest approach, silhouetting Pluto's limb against solar light. The haze was not a single layer. It was multiple layers, more than a dozen of them, each one a thin stratum of particles suspended at a different altitude, extending together to heights of 200 kilometers or more above the surface. Each layer was composed of particles smaller than the wavelength of visible light, formed when ultraviolet radiation from the sun fell on the nitrogen and methane gas that makes up most of Pluto's atmosphere, breaking the molecules apart and driving a slow, continuous chemistry that reassembled their fragments into more complex organic compounds. These compounds are called tholins, a word coined decades ago for the dark, sticky, polymer-like materials that form when radiation acts on simple organic gases. In Pluto's atmosphere, they form at altitude and then drift slowly downward, settling onto the surface across long stretches of time and giving the terrain outside the bright basin its reddish-brownish cast. Pluto's atmosphere is thin. The total pressure at the surface, from all that nitrogen and methane and the trace of carbon monoxide above it, is roughly 100,000 times less than the air pressure at sea level on Earth. If a person could somehow stand on Pluto's surface, which for many reasons they could not, the atmosphere above them would not register on any ordinary pressure gauge. It would be less than nothing to breathe, less than the near vacuum inside the most advanced industrial pump. And yet it is enough. It is enough to scatter blue light and produce a sky that in images from New Horizons, taken after the closest pass, appears faintly, unmistakably blue, the same physics that makes Earth's sky blue, operating in an atmosphere so thin it is barely there at all, producing its hue in a place where the sun is a dot. The closest approach happened on the 14th of July, 2015. The spacecraft passed within 12,500 kilometers of Pluto's surface, moving at a speed that covered that distance from closest approach to retreat in a matter of minutes. The instruments were open for the entire encounter, recording temperatures, chemical compositions, magnetic environments, particle densities, and image after image after image of a surface no instrument had ever resolved before. The scientists and engineers watching from Johns Hopkins University Applied Physics Laboratory in Maryland, where the mission team was gathered, knew that the encounter was happening. The telemetry that would confirm the spacecraft had survived and returned its data would take approximately 4.5 hours to cross the distance at the speed of light, and the spacecraft had been placed in a pre-programmed observation mode that would prevent it from communicating with Earth during the approach and encounter itself. There was nothing to do but wait. 4.5 hours is a short time in the history of a planetary mission. It is a long time in a room full of people who have spent 9 years working toward a single day. When the signal arrived and the confirmation ran through the room, the spacecraft was functional. The instruments had operated, the data was stored, and the transmission could begin. The response was what one would expect from people who had committed a decade of their professional lives to a single pass of a small machine past a body that had never been seen up close. It was not a quiet room. For a while, the data did not come back all at once. It could not. The transmission rate from New Horizons at that distance was limited by physics and the size of the spacecraft's antenna and the capabilities of the receiving dishes on Earth to something very slow, measured not in gigabytes per second, but in kilobits, smaller by many orders of magnitude than the data rate of an ordinary household internet connection. The full data set from the encounter would take more than a year to download completely, image by image, instrument reading by instrument reading, the record of a single pass being slowly unwound across the long, quiet months following the encounter itself. Each new image arrived as one piece of a picture that was assembled gradually, each piece adding a region or a detail or a resolution that had not existed in any human record before. The mountains arrived in one set of images. The convective cells of Sputnik Planitia arrived in another. The haze layers came back in a sequence of observations taken during the long hours after closest approach, when New Horizons was already receding, already moving away from Pluto at the same speed it had arrived, the bright basin and the mountains and the reddish plains all shrinking back into the dark behind it. Each image downlinked to Earth required planning, scheduling, patience. Each one was a small transmission from a machine that had gone somewhere no machine had gone before, and the patience required to receive it was of a piece with the patience required to send it. The understanding that crossing enormous distances in any direction, even at the speed of light, simply takes time, and that time spent waiting for a signal from the outer solar system is not wasted time. It is the time it takes to know a new place. In the months after the flyby, As images and data continued to download, the picture of Pluto that assembled itself was in many ways not what the scientists had been modeling. The nitrogen plains had been hypothesized, but their smooth youth had not. The mountains had been expected to be smaller. The haze layers had not been predicted at their observed thickness and number. The reddish surface coloring of regions outside the bright basin was more varied in tone and extent than the pre-encounter models had suggested. And the heart shape itself, visible in approach images so early that it became a point of reference and a kind of symbol for the whole encounter, had not appeared in any simulation of how Pluto's surface might look. A place that had been a dot of light, a point on a photographic plate, a quantity measured indirectly, had become a world, not a type, not a category, not a population member, a world with specific geography and specific geology and an atmosphere with specific chemistry and specific structure, a body that had been doing what bodies in the solar system do, forming and cooling and resurfacing and losing volatiles to space and accumulating tholins on its plains for billions of years before anyone on Earth knew it existed. The spacecraft that revealed it did not stop there. It had no mechanism for stopping. Its trajectory carried it onward, past the bright basin, past the mountains, past the dark hemisphere of Pluto that New Horizons never fully saw, and into the deeper outer solar system, still moving at more than 50,000 kilometers per hour relative to the Sun, still sending telemetry back across the growing gap between itself and the nearest receiver, the signal weakening by the inverse square law with every kilometer of additional distance, taking longer each month to arrive. New Horizons was aimed after Pluto toward a smaller, stranger body in the outer reaches of the Kuiper Belt, a mission extension that would take it 3 more years of travel and allow its instruments to examine a frozen object that had been sitting undisturbed at the edge of the solar system since before the planets themselves were fully formed. That encounter happened on the first day of 2019, but in the months and years between the Pluto flyby and that second destination, the spacecraft moved through regions that no human object had ever crossed, its instruments still open, still measuring the particle environment and magnetic conditions of the outer solar system, still returning data from distances that make the notion of real-time communication feel like a comfortable fiction that the universe doesn't actually support. The data from Pluto itself continued to come in across the first year and more after the flyby. Scientists worked through the images, cataloging features, analyzing spectra, comparing observations from different instruments, fitting the readings into models of how a body at that distance, with that composition and that size, would behave over geological time. Some of what they found fit well with the models they had built. Some did not. The convective overturn of Sputnik Planitia fit the physics of nitrogen ice well enough, once the calculations were run properly. The mountains fit the structural properties of water ice well. The haze layers fit the photochemistry of nitrogen-methane atmospheres, more or less. But the overall freshness of the surface, the youth of Sputnik Planitia in particular, required explanation, some mechanism that had been resurfacing this world and keeping it geologically active much longer than would be expected for a body of its size at its distance from any significant heat source. The best current picture involves a combination of internal radiogenic heat, the convective cycling of the nitrogen ice itself, and possibly the accumulation of additional nitrogen ice over time as volatile materials cycle across Pluto's surface in step with its seasons. Pluto's seasons run on its orbital period of approximately 248 Earth years, a year so long that within it, Pluto moves from a perihelion where its surface is slightly warmer and its atmosphere slightly thicker, to an aphelion, where the atmosphere largely freezes out and falls onto the surface as frost, and then back again. Within that enormous seasonal cycle, volatiles migrate across the surface. Regions that were bright grow dark. Regions that were dark brighten, the heart-shaped basin filling and draining its nitrogen ice, like a tide measured not in hours, but in centuries. This is not a world that simply sits still and grows cold. It moves, it cycles, it changes on timescales that human observation has barely scratched. New horizons passed once, in a matter of hours, and captured one frame from one moment in a process that has been running for 4 billion years. The full library of Pluto's history would require a patience of observation that no human institution has yet developed the tools to exercise. And the data from that single pass is still being worked through, still being analyzed, still yielding interpretations that were not possible in the months immediately after the encounter. Science does not always move in a clean line from observation to conclusion. Sometimes an observation sits in the record for years before a question comes along that it can answer. The images of Pluto's haze layers, the spectra of its surface ices, the altitude profiles of its atmosphere, the texture of its nitrogen plains. All of these are still open, still being incorporated into models of how the outer solar system works and how small icy bodies evolve across deep time. The flyby ended. The analysis did not. Somewhere beyond Neptune, at this moment, New Horizons continues to move outward. Its nuclear power source is decaying slowly, its available electrical budget shrinking year by year, its instruments operating at reduced capacity compared to what they managed at Pluto. The team that monitors it has learned to prioritize, to choose which measurements justify the power expenditure, to husband the remaining capability of a machine that cannot be refueled or repaired, and that will, within a relatively small number of years, go silent for the last time in its long journey outward. When it does, it will still be moving. It will still be on its course. It will pass through the heliopause, the outer boundary, where the sun's influence gives way to the broader medium of interstellar space, and it will continue beyond it into a region that is no longer any planet's neighborhood, no longer the solar system in any functional sense, simply space, deep space, in which the sun is a bright star and the planets are invisible, and the only human artifacts present are 4 small machines that left Earth decades ago and found no reason to stop. What New Horizons sent back from those 4.5 hours near Pluto rests in archives and in the papers published from them, in the texture of images that can be examined on ordinary screens by anyone who wants to look, images of a real surface, in real light, on a real world, that for the entirety of human history, before July 2015, was nothing more than a faint point of movement on a photographic plate, a calculated position on a chart, a body known only by what could be inferred at enormous remove. The images made it specific. They made it a place, and places, once seen, carry a different kind of weight than abstractions ever can. Pluto's surface receives the faint light of a far sun and reflects part of it back out into space in all directions. Some of that reflected light, after traveling 4.5 billion kilometers, arrives at Earth. Some of it falls on telescopes. Some of it carries information about the chemistry and albedo of a surface that has never been walked on and may never be walked on, and that was, for the whole of its 4 billion years, before one January morning in 2006, entirely unknown, entirely patient, and entirely unchanged by whether anyone knew it was there or not. The spacecraft has moved on. The data continues to arrive, slowly, one packet at a time, crossing the outer solar system at the speed of light and arriving on Earth hours after it was sent, carrying the last transmissions of an encounter that lasted hours and produced a record that scientists will spend careers working through. The bright basin rests on Pluto's surface in slow convective motion. The mountains stand at its edge in frozen water. The haze hangs in thin layers above the plain, blue in the sunlight that reaches this far, building layer by layer from the molecules of a nearly empty atmosphere. And somewhere beyond all of it, still moving, still faintly warm with the heat of its own slow nuclear decay, the spacecraft continues outward into the dark, its antenna pointed back across the enormous distance toward a world it briefly touched and from which it will never return. The signal it sends home, growing fainter and slower and more stretched across time with every year that passes, like a voice continuing to speak long after the speaker has gone somewhere you cannot follow. From the frozen surface of Pluto, in the direction of a specific point on the horizon, something hangs in the sky that does not move. It does not rise. It does not drift. It does not trace an arc through the stars, the way any moon does when seen from any other world. It simply hangs there, fixed above one particular stretch of ice, as it has hung for as long as there has been a sky to hang in. Half the width of the sky it covers, a pale gray-brown sphere, so close and so large that the eye would need to travel across it, the way an eye travels across a landscape, not a single glance but a slow sweep from one curved limb to the other. This is Charon, and nothing about the relationship between these two worlds is like anything else in the solar system. The reason Charon never moves across Pluto's sky is the same reason Pluto never moves across Charon's. Both worlds have locked their rotation to each other across billions of years of gravitational patience. Pluto turns on its axis once every 6 days and 9 hours. Charon completes one orbit in exactly the same time. The two bodies have been worn into this synchrony, each pulling on the other's slight asymmetries, each slowing and settling into the only configuration where the pull finally, permanently rests. Neither world has rotated away from the other since before the solar system's first billion years were done. On Pluto's near side, Charon fills the sky above a single fixed point. On Pluto's far side, Charon has never been visible at all. The far hemisphere has faced away from Charon for so long that no amount of waiting would ever bring it into view. Two entire hemispheres of an entire world divided by this single gravitational fact, one face always bathed in whatever faint reflected light Charon carries, the other always in a sky where Charon simply is not. The distance between them is 19,570 kilometers. At that range, on that scale, the two bodies are close enough that their shared gravitational arrangement has produced something that has no real parallel nearer to the Sun. The point around which both worlds orbit is not at the center of Pluto. It is not inside Pluto at all. It floats in open space, roughly 960 kilometers above Pluto's surface, an invisible hinge in empty air, around which both bodies wheel in their locked and mutual dance. This arrangement, where a shared orbital center sits outside both bodies, has a technical name, though the name matters less than the image it produces. Pluto and Charon are not, in the most precise sense, a planet and its moon. They are a binary, two worlds of different sizes orbiting each other, bound together by gravity across open space, each one the other's permanent sky. Charon is more than half as wide as Pluto. No other large moon in the solar system is so proportionally large relative to the body it accompanies The difference in size is real, but it is not overwhelming. Charon is darker than Pluto, grayer and more muted, its surface telling a different chemical story. Where Pluto's bright regions glow with nitrogen frost and methane ice, Charon's surface is mostly water ice, overlaid with a more neutral palette, marked in most places by a quiet, uniform gray that speaks of old, unrenewed terrain. But one region of Charon does not look like the rest. At its north pole, a stain spreads across the surface in shades of deep rust and reddish brown, dark against the gray plain surrounding it, large enough to be visible even in the first images returning from a distant spacecraft. This polar region has a name now, Mordor Macula, and the color it carries did not form in place. It came from somewhere else. It arrived on the wind, if wind is a word that can be used for the thin, slow movement of molecules escaping one world's gravity and drifting, unhurried, across the gap to another. Pluto's atmosphere is extremely thin, 100,000 times less dense than the air at sea level on Earth, and it leaks slowly into space. Methane molecules escape from Pluto's uppermost atmospheric layers and drift outward. Some of this escaping gas eventually reaches Charon. In Charon's deep polar winter, which lasts for decades at a time, the temperature drops low enough that the arriving methane does not bounce away. It freezes directly onto the polar surface, building up a thin coating of methane frost across the winter cap. That frost sitting on the exposed surface of an airless world is then bathed in ultraviolet radiation from the sun and from the charged particles that stream in from outside the solar system. Radiation breaks the methane molecules apart and reassembles the pieces into heavier, more complex compounds, dark, reddish organic materials known as tholins. And when the long polar winter ends and the frost eventually sublimes away, the tholins remain. They are too heavy to evaporate easily. They stay. Season after season, across deep time, the layer of tholins thickens and darkens, and the cap builds its color from Pluto's own escaped air, chemically transformed and deposited across millions of years onto the surface of a neighboring world. There is something in this that is difficult to name cleanly. Two worlds, separated by nearly 20,000 kilometers of empty space, sharing material across that void through nothing more than the ordinary drift of gas and the pull of cold. Pluto breathes its atmosphere slowly out into the dark, and Charon catches what comes and wears it for an age and is colored by it. The redness at Charon's pole is a record of proximity. It is what it looks like when two worlds have been close enough, for long enough, for one to leave its mark on the other. The five-body system that contains both Pluto and Charon was built in a single violent event, and the evidence is still written in the orbits of the four smaller moons that trace their paths around the binary pair. Nix, Hydra, Kerberos, and Styx, four names taken from the mythology of the underworld, following the tradition established when Charon was first named, orbit the Pluto-Charon center of mass, in the same plane, the same direction, at distances ranging from roughly 48,000 kilometers to nearly 67,000 kilometers out. The flatness and alignment of their orbits, all four lying in the same disk and moving the same way, carries the signature of a common origin, and that origin, according to the best current picture, was a collision. Roughly 4 billion years ago, a large object struck the early Pluto with enough force to throw enormous quantities of debris into orbit around the remains. The fragments that gathered into Charon were large and close. The smaller bodies that eventually became Nix, Hydra, Kerberos, and Styx were built from the outermost, lighter debris, all five moons consolidated from the same event, out of the same material, in the same plane and have been orbiting together ever since. The system is not assembled from objects gravitationally captured over time. It was made all at once in a moment of enormous energy and has been settling slowly into its current configuration ever since. Nix is a small, irregular body, broader across one dimension than the others, coated in nearly pure water ice that gives it an unexpectedly high reflectivity. Styx is the smallest of the four, faint enough that it was not detected until 2012, more than 3 decades after Charon was found, despite being in the same well-studied system. Kerberos, which was expected from theoretical models to be relatively dark based on its mass, turned out instead to be coated in bright water ice, a surprise that required revising the models that had predicted it. Hydra is the farthest out of the four, and Hydra spins, not in the measured, settled way that a tidally locked moon spins, slowly, once per orbit, the same face always forward. Hydra spins the way a thing spins, when the forces acting on it have never fully settled into agreement. It rotates 89 times for every single orbit it completes around the Pluto-Charon pair. Its spin axis is tilted roughly 110 degrees relative to its orbital plane, which means it is not simply rotating quickly in the ordinary sense, but tumbling, its poles sweeping wide arcs across space as it goes, its surface catching sunlight from one direction, and then another, in a sequence that does not easily repeat. The reason for this tumbling is the gravitational complexity of the environment Hydra inhabits. Orbiting a binary system means feeling not one gravitational pull, but two, and those two pulls shift in their relative direction and strength, as Pluto and Charon wheel around each other on their 6-day cycle. For a small, irregular body like Hydra, the torques produced by this constantly shifting gravitational landscape are enough to prevent any stable rotation from taking hold. There is no tidal lock to settle into, because the force demanding that lock is never pointing in the same direction for long enough to win. Hydra tumbles, and has been tumbling, and will go on tumbling as long as it orbits a binary, which is to say, indefinitely. The surface of Hydra, in the images that arrived from a distance of some hundreds of thousands of kilometers, appeared coated in water ice, clean, bright water ice, largely unprocessed by the radiation that darkens and reddens surfaces elsewhere in the outer solar system. Why Hydra's surface should be so clean is not fully settled. One possibility is that micrometeorite impacts, which over time tend to darken surfaces by mixing in carbonaceous material from impacting objects, might be offset on Hydra by its tumbling motion, distributing impacts across a wider and more varied surface. Another possibility involves the source and rate of incoming debris. The answer may be simpler than any current model suggests, or more complex. The data is real. The interpretation is still open. To stand on Hydra, which is to say, to imagine a surface so small and so weakly gravitating that a person could leap from it without effort and look inward toward the center of the Pluto-Charon system, would be to see the binary pair as two distinct disks of light, one larger and brighter, one smaller and darker, each moving relative to the other over a cycle of roughly 6 days. The larger one, Pluto, would glow with the reflected light of a sun reduced to a very bright point of light at this distance, its surface patterned with regions of different brightness. The smaller one, Charon, would hang nearby, the two bodies rising and setting together from the perspective of Hydra's own slow orbital motion, but never still relative to each other. The entire system is extraordinarily small, not in the sense that any of its individual bodies are unremarkable in size. Pluto alone is 2/3 the diameter of Earth's moon, and Charon is proportionally enormous, but in the sense that the whole assembly, 5 bodies, all their orbits, the entire gravitational architecture of the Pluto system, would fit comfortably inside the orbit of Earth's own moon, with room to spare. The widest orbit in the Pluto system, traced by Hydra, reaches out to roughly 67,000 kilometers. The moon orbits at roughly 384,000 kilometers. Every moon, every orbit, every trajectory in the entire Pluto system fits in the space between the Earth and Moon more than 5 times over. And yet this compact nested arrangement of 5 bodies occupies a volume of the outer solar system largely defined by empty space. The nearest significant object to the Pluto system in the broader context of its region is not particularly near. The solar system at these distances is not crowded in the way the inner planets are crowded. It is spread, and Pluto's system drifts within that, spreading with no close neighbors, no perturbing bodies, large enough to unsettle it on human timescales, its 5 members locked into their ancient arrangement and continuing it quietly. The tidal locking between Pluto and Charon is worth sitting with for a moment because it involves a kind of time that is difficult to hold steadily in mind. Tidal locking happens because of friction. When a moon is first placed in orbit, or when 2 bodies first form close together after a collision, the gravitational pull of the companion raises a slight tidal bulge on each body. If the body is rotating faster than it orbits, the bulge is dragged slightly ahead of the direct line between the 2 bodies by that rotation. The companion's gravity pulls backward on the leading bulge, exerting a torque that acts against the rotation, slowing it. This happens continuously over geological time, dissipating the body's rotational energy as heat. For our moon, this process took perhaps 1 billion years. For Charon, so large relative to Pluto and so close, it happened faster. For Pluto, being tugged by a body as proportionally massive as Charon, the process works simultaneously from both directions. The result is a system where both members have shed their independent rotation entirely and settled into the single frequency that allows them to always face each other. The Pluto of 4 billion years ago may have spun in something close to a day of a few hours. That faster rotation is entirely gone. The energy it carried has been turned to heat, dissipated into the interior, and released. What remains is the slow, locked, paired rotation of a 6 1/3 day cycle that is simultaneously a day, an orbital period, and a kind of shared year for the system as a whole. From any point on the hemisphere of Pluto that faces Charon, there is no day. There is no night in the ordinary sense either. Charon moves through no cycle above the horizon. It is simply there, the same hemisphere always presented, the same face always visible, and what changes is only the lighting, the faint distant sun crossing the sky on its annual track, the stars wheeling slowly overhead, the background light of the Milky Way, faintly visible in a sky where the sun, at this distance, provides less than 1,000th of the illumination it provides at Earth. The hemisphere of Pluto that faces away from Charon has a different quality of emptiness. That sky carries no large companion. The sun traces its path. The stars move. And Charon is never visible, not in any season, not at any time of Pluto's long year, because the far side of Pluto has been facing away since the tidal locking was complete, and the universe does not make exceptions. There is a kind of duration in all of this that the Pluto-Charon system carries simply by existing. These 2 worlds are not young. They formed from the same collision event, roughly 4 billion years ago, and in the 4 billion years since, this is what they have been doing, orbiting each other, facing each other, slowly exchanging the faintest traces of material across the gap between them, building the rust-colored polar cap on Charon molecule by molecule, wearing the surfaces of the small outer moons into their current tumbling states, and continuing. 4 billion years is long enough that the mind does not genuinely hold it, but instead holds a symbol for it, a number without true weight. A more useful measure might be this. In the time that Pluto and Charon have been locked together, the continents of Earth have assembled and broken apart and reassembled multiple times. Life has moved from single cells to every form currently breathing, or swimming, or pressing its roots into the soil. The sun has aged measurably. The asteroid belt has been stirred and sorted. The outer planets have migrated to some degree from their original positions. And through all of this, the same face of Pluto has been pointing at the same face of Charon, and the same face of Charon has been pointing back. The small moons spin in the outer regions of this arrangement and carry a different kind of record. Where Pluto and Charon carry the record of long stability, the small moons carry the record of complexity. Their tumbling rotations are not a sign of disorder, but of balance, or rather of the precise insufficiency of any single stabilizing force. They tumble because the binary's gravitational environment contains too many competing rhythms to settle into any one of them. Hydra's 89 rotations per orbit is not a sign of energy running loose. It is the natural response of an irregularly shaped body in a place where the tidal forces are always shifting. The 4 small moons also have an additional structural relationship to each other that speaks to their common origin. Their orbital periods are close to integer ratios with each other and with Charon. Styx, Nix, Kerberos, and Hydra orbit at periods of roughly 20, 25, 32, and 38 days, respectively, and these periods carry near resonances, not perfect resonances, but echoes of them, that the original collision and the subsequent gravitational evolution of the system have produced and preserved. The system retains the memory of the event that made it, written in the spacing of orbits, the way a set of ripples expanding in water retains the size and shape of the stone that made them long after the stone is still. The water ice coating the small moons is also a detail worth noticing. Water ice is not the dominant surface material on Pluto, where nitrogen and methane and carbon monoxide ices define the bright active terrains. On Charon, water ice is the primary surface component, less reflective and more muted, but Nix and Hydra are almost entirely water ice on their surfaces, and this is consistent with their having been built from the outer debris of the collision, material thrown far enough from the impact that it was enriched in the water ice of Pluto's mantle rather than the volatile ices of Pluto's surface layers. The collision was energetic enough to strip and scatter the outer structure, and the composition of the small moons reflects where in that scattering each body formed. To hold the whole system in mind at once is to hold a set of concentric relationships. At the center, 2 worlds facing each other across a gap of 20,000 kilometers, their shared orbital point floating in empty air between them, each showing the other the same hemisphere it has shown for billions of years. Around them, at distances stretching to 67,000 kilometers, 4 small irregular bodies tracing nearly circular orbits in the same flat plane, 2 of them roughly known since the late 1980s, 2 found only in the last 15 years, because the instruments needed to see them at such faint brightnesses had not existed before. The whole assembly held together by gravity, tilted relative to the solar system's main plane, orbiting the sun on a path that carries it from inside the orbit of Neptune at its closest approach to nearly 50 times the Sun-Earth distance at its farthest. The tilt matters. Pluto's orbital plane is inclined about 17 degrees relative to the plane in which the other large planets orbit, a larger tilt than any of the 8 recognized planets, a tilt that carries it into and out of the ecliptic plane on the time scale of its 248-year orbit. The tilt is part of what marks Pluto as a different kind of body from the large planets, not inclined much by planetary standards, but inclined enough to trace a noticeably different path, one that periodically carries it through regions of the Kuiper belt at angles that the other planets do not experience. Pluto is a Plutino. This is a technical name, but it carries real physical meaning. Pluto is in a resonance with Neptune, a gravitational relationship in which Pluto completes 2 orbits of the Sun in the time Neptune completes 3. This resonance is not coincidental. It is the reason Pluto survives in its current orbit without being gravitationally ejected or sent inward toward the Sun over millions of years. The resonance acts as a protective structure, arranging the orbit so that Pluto and Neptune are never close to each other at the same time, even when their paths cross on paper. Neptune is always somewhere else in its orbit when Pluto is near the crossing point, and this perpetual near miss keeps the smaller body stable across timescales that would otherwise see it disturbed beyond recovery. Pluto shares this resonance with many other objects in the outer solar system. They are all Plutinos, but Pluto was the first found, the largest of them, and the one whose orbit carries all the history of its system's resonant relationship with the most distant of the large planets. The relationship with Neptune is distant, but it is real. It has been maintained for billions of years. It shapes the orbit. It determines the geometry of every closest approach and every farthest recession. It is one of the invisible structures running through the outer solar system, connecting bodies that never come near each other, holding them in stable arrangements through nothing more than the mathematics of recurring orbital rhythms. Beyond the resonance, beyond the orbit, beyond even the widest reach of Hydra's slow circuit, the Pluto system is surrounded by the dark. The sun is bright at this distance, brighter than any star, clearly the dominant light source, but its warmth arrives as a faint suggestion rather than a temperature. The surface of Pluto is among the coldest places in the solar system, the temperature sitting around 230 degrees below zero on the Celsius scale, a cold so far below ordinary human experience that comparisons begin to lose their grip. Water ice at that temperature is not soft or yielding, but as rigid and structural as granite. The nitrogen and methane ices that cover much of Pluto's bright terrain are soft by comparison, capable of slow creep and flow on geological timescales, but even they are far colder than anything encountered naturally on Earth. In this cold, under a sun reduced to a brilliant star, the 5-body system continues its arrangements. Pluto and Charon face each other on their 6-day cycle. The 4 small moons trace their orbits, tumbling, reflecting what faint light reaches them. The thin atmosphere of Pluto, which expands slightly when Pluto is nearer the Sun and contracts as it moves away, exhales its slow leak of methane and nitrogen molecules into the space around the system. Some of those molecules drift outward, some are lost to space entirely. Some reach Charon's polar regions when the geometry is right, settle in the cold of deep winter, and begin their slow chemical transformation into the dark reddish tholins that build the polar stain across centuries. This exchange has been happening since shortly after the system formed. It will continue as long as both bodies retain their current composition and their current orbital relationship. There is no mechanism in place to end it on any timescale that means anything in human terms. Mordor Macula will be darker in 1,000,000 years than it is now, built slowly thicker with each polar winter, each spring sublimation, each quiet deposit of transformed material settling back to rest. The Pluto system does not need to be visited to be doing what it does. The five bodies orbit and face each other and tumble and exchange material, regardless of whether anything in the inner solar system takes any notice. The science that has described these things, the tidal locking, the resonance with Neptune, the chaotic tumbling of the outer moons, the molecular transfer painting, the polar cap, comes mostly from the brief passage of a spacecraft that crossed through the system in a matter of hours, supplemented by decades of careful observation from Earth and from the patient theoretical work of understanding how gravity shapes small bodies over long time. What the images and the data carried back was not a full picture. It was a narrow slice in time, a moment of closest approach, from which much has been inferred and much more remains genuinely uncertain. The interior structures of Pluto and Charon are not fully known. Whether there is or was ever liquid water beneath Pluto's outer ice remains an open question. The surface deformation patterns suggest it is possible, and the numbers allow for it, but no definitive evidence exists. The precise history of Hydra's tumbling state and how long it has been in its current configuration is not pinned down. The exact process by which the Pluto-Charon binary formed from the initial collision debris is still being refined. What is known is the broad shape of the thing, two worlds facing each other across open space, bound in permanent mutual gaze, surrounded by four tumbling fragments of their violent birth, all of them settled into a slow and ancient stability at the edge of the region where the sun still dominates. The system is old, it is quiet, it moves on its 248-year orbit without haste, without any sense that the motion is directed toward anything in particular. It is simply the motion continuing, as it has been continuing, as it will continue for longer than the words used to describe it are likely to last. Charon hangs in the sky above the fixed point on Pluto's surface where it has always hung. Pluto hangs in Charon's sky above the fixed point on Charon's surface where it has always hung. Between them, the invisible shared orbital center traces its 6-day loop in empty space. And beyond the outermost of the small moons, beyond the last of the tumbling fragments, the dark of the outer solar system extends in every direction, vast and still, carrying the system forward in its long ellipse around a sun that is, from here, only the brightest thing in a sky full of quiet, steady light. The small moons spin in the outer dark of the Pluto system. Hydra turns on its tilted axis, catching light from one angle and then another, its surface of clean water, ice neither accumulating nor eroding on any time scale that matters here. Kerberos holds its small shape against the black. Nyx drifts in its near-circular path, its bright surface reflecting back into space the same faint sunlight that has been crossing these billions of kilometers and arriving at these icy surfaces since before the first living thing on Earth drew breath. Styx, faintest of all, completes its orbit as it has completed every orbit since the debris of the ancient impact settled and gathered and became something that has a name now, a name given to it long after it began. Their tumbling is not disorder. It is the signature of an old collision, still written in the spin of fragments, still legible to anyone patient enough to watch and measure and think, a kind of deep record that the bodies themselves carry forward, unchanged, into whatever comes next. From a great enough distance, the solar system looks almost simple. There is the sun, there are the planets looping in their orderly rings. And then, beyond the last of them, there appears to be nothing, a long dark emptiness stretching outward to where the stars begin. That appearance is wrong. Beyond the orbit of Neptune, beginning at roughly 30 times the Earth's distance from the Sun and spreading outward for another 20 times that distance again, there lies a vast flattened ring of space, so wide that light itself takes more than 6 hours to cross from one edge to the other. It is not empty. It has never been empty. It holds hundreds of thousands of icy bodies, perhaps more, drifting in the cold and the dark, in orbits so slow and so distant that most of them will never be named, never be counted, never be individually known. Seen from above, at a scale large enough to take in the full width of the outer solar system, this ring has a faint, diffuse presence, like the memory of a disk. It is what is left of the material that built the planets, the cold outer remnant of the same cloud of gas and dust that billions of years ago gathered itself around the young sun and slowly sorted into everything the solar system now contains. The inner material fell together into rock and iron, the outer material too cold and too spread out to build anything as dense as a planet, remained as it was, loose, icy, and countless. This is the Kuiper Belt. The 8 planets fit inside a circle 30 times the size of the Earth's orbit. The Kuiper Belt begins where that circle ends and spreads outward from there like a great cold disk surrounding the compact brightness of the inner solar system. Across that disk, scattered at distances so vast that even fast light moves slowly through them, the bodies of the belt drift in their ancient, unhurried paths. Most of them are small. Most of them are dark. Most of them have been circling the sun since before the Earth had an ocean, and they will still be circling it long after the sun has changed beyond recognition. They are the patient ones, the leftover ones, the ones that the early solar system had no further use for and simply set aside. For most of recorded history, no one knew they were there. The first hint that something lay beyond Neptune came not from observation, but from mathematics. Neptune itself had been found that way, its gravity tugging gently on Uranus, its presence deduced before any telescope found it. After Neptune was confirmed, some astronomers wondered whether the small deviations remaining in the outer planet's motions might point to something else, something farther out. The searches that followed were long and largely unrewarded. Pluto was found in 1930, but Pluto alone could not account for the predicted mass. The belt itself, the actual population, the hundreds of thousands of smaller bodies that make up the true outer solar system, remained invisible, not because the instruments were wrong, but because the objects were simply too faint and too far away for the technology of that era to detect. Once the idea that a belt of such objects might exist had been proposed theoretically in the decades following Pluto's discovery. The thinking was this: the solar system formed from a disk of material. The inner disk built planets. The outer disk should have left something behind, some population of smaller primordial objects too distant from the sun to accumulate into anything larger. Comets were one piece of evidence. Short-period comets, the ones that swing through the inner solar system on orbits lasting only a few centuries, had to come from somewhere, and the outer solar system seemed the most plausible source. But the belt itself was theoretical, a mathematical expectation, a gap in the inventory of known things, waiting for the instruments to catch up with the prediction. On the night of August 30th, 1992, at the summit of Mauna Kea in Hawaii, 2 astronomers named David Jewett and Jane Liu were using the University of Hawaii's 2-meter telescope to search the outer darkness with unusual patience. They had been searching for years, scanning star fields for the slow, faint drift of any object moving against the background at the speed that a trans-Neptunian body would move. Most nights yielded nothing. That night yielded something. A single faint point of light, moving too slowly for a main belt asteroid, too far for anything already catalogued, drifting at the pace of a world in the outermost reaches of the solar system. It was given the designation 1992 QB1, a provisional label in the dry language of orbital mechanics. Decades later, it received a proper name, Albion, but on that night it was simply a dot, a slow-moving dot, the first of its kind ever directly observed. The Kuiper Belt had been found, not as a theory, but as a thing. What followed was the long methodical work of counting. Albion opened a door. Within a few years, more objects appeared on survey plates, then dozens, then hundreds. The instruments improved, the surveys widened, and the outer solar system began to reveal itself as something far more populated than anyone had expected. The objects came in different orbits, different sizes, different colors, different compositions. And as the census grew, patterns began to emerge, patterns that told, slowly, and in the language of orbital mechanics, a story about the early history of the solar system itself. Two broad families of Kuiper Belt objects are now recognized, distinguished by the character of their orbits. The cold classical objects, cold here referring not to temperature, which is cold enough throughout the belt, but to the mathematical temperature of their orbital motion, travel in nearly circular paths at low angles relative to the plane of the planets. Their orbits are calm, their paths are wide and unhurried and close to perfectly round, and this calmness is significant because it suggests they have not been disturbed. These objects appear to have formed where they now orbit, accreted slowly from the disk material in the earliest centuries of the solar system, and settled into their quiet circular paths without ever being significantly pushed or pulled by anything larger than themselves. Their surfaces tend to be reddish, heavily processed by billions of years of radiation, but never refreshed by the kind of geological activity that would expose fresh material from below. They are old and still, and largely unchanged, fragments of the earliest outer solar system preserved in the cold. The hot classical objects are different. Their orbits are eccentric, tilted at steep angles to the planetary plane, scattered across a wider range of distances from the Sun. They move with a kind of orbital agitation that the cold classicals lack. This agitation is not random. It is the signature of a disturbance, a record of something that happened long ago and altered their paths. The leading picture is that the giant planets, early in the solar system's history, did not orbit where they orbit now. They migrated. Neptune, in particular, is thought to have moved outward from a closer starting position, its gravitational influence sweeping through the outer disk like a slow tide, flinging some objects inward and others into the higher, more inclined orbits that the hot classicals now occupy. The difference between the two populations, written in the geometry of their paths, is one of the clearest records the solar system has kept of its own turbulent early life. And then there are the Plutinos. Pluto itself belongs to this third family, and the family takes its name from Pluto, which was its best-known member long before the others were catalogued. A Plutino is an object trapped in a gravitational rhythm, with Neptune, a rhythm so precise and so stable that it has persisted for billions of years without breaking. For every 2 orbits a Plutino completes around the Sun, Neptune completes exactly 3. The ratio is 2 to 3, and it is not a coincidence, it is a resonance, a condition in which the mutual gravitational influence of Neptune and the smaller body reinforces itself over and over, nudging the smaller body back into line each time it begins to drift. The rhythm is self-correcting. It is, in its way, one of the most patient things in the solar system. Two bodies, one enormous and one small, locked into the same gravitational dance for the age of the solar system, neither one escaping, neither one gaining or losing ground. In Pluto's case, the resonance plays out across an orbit of 248 years. Neptune's orbit takes just under 165 years. Over time, the two bodies complete their laps in a ratio that stays exactly and permanently at 2 to 3. They never quite meet at the same point in space at the same time. The resonance is constructed precisely to prevent that, and so for all the apparent closeness of their gravitational relationship, Pluto and Neptune never come dangerously near each other. The resonance is not a trap, it is a shelter. Pluto orbits in safety because of Neptune, held in its steady path by the same force that might, in a different configuration, have expelled it from the solar system entirely. The existence of the Plutino population is one of the clearest pieces of evidence that Neptune migrated outward. For so many objects to be caught in the 2 to 3 resonance, Neptune must have swept through the outer disk slowly enough to capture them one by one, its resonance acting like a net moving through water, gathering objects as it passed. A planet that had always occupied its current orbit would not have accumulated so many resonant companions. The population of the Plutinos is, in this sense, a record of a journey, a planet's long migration outward, captured in the orbits of the smaller bodies it gathered along the way. Beyond the resonant populations, the belt holds something even harder to count, the simple majority, the classical bodies that orbit in the wide middle of the disk, without any special relationship to Neptune or to each other, moving in paths that are neither perfectly circular, like the cold classicals, nor as eccentric as the scattered objects beyond. They are the background population, the unremarkable majority, and they are hundreds of thousands strong in the size range alone that present surveys can detect. Below that threshold, in the size range of objects too small for current telescopes to find at Kuiper Belt distances, the number grows larger still. The full population of the belt is unknown. What is known is that the known population is a fraction, a significant but incomplete sample of a far larger whole. The numbers are worth sitting with, not as a performance of how large they are, but as a simple fact about what the outer solar system contains. Estimates of the number of Kuiper Belt objects larger than 100 kilometers across, roughly the size of a moderate asteroid, run to more than 100,000. The asteroid belt between Mars and Jupiter, which most people think of as the solar system's main reservoir of small bodies, contains fewer than 2,000 objects of that size. The Kuiper Belt is not empty. It is not sparse. It is, by the count of its members, one of the most populated regions of the solar system, hidden from ordinary perception only by the extreme distances involved and the faintness of objects that receive sunlight, so dilute that even ice-bright surfaces glow only dimly against the dark. Light from the sun, which reaches Earth in 8 minutes, takes more than 4 hours to reach the inner edge of the Kuiper Belt. At the belt's outer edge, that same light has been traveling for more than 6 hours. The objects there, the cold classicals drifting in their ancient circles, the Plutinos locked in their patient resonances, the hot classicals scattered across higher orbits, all of them exist in a kind of permanent deep dusk, a light so attenuated and so distant from its source that it is less warmth than memory. Surface temperatures across the belt sit at roughly 40 degrees above absolute zero, which is cold enough that most gases freeze solid. Nitrogen, carbon monoxide, methane, things that flow as liquids or drift as vapors in warmer parts of the solar system, are stone hard here, locked into the surfaces of these small worlds as permanent frost. What volatility exists in any of these objects has been frozen in place for most of the solar system's age. That cold, that stillness, that preservation, these are what make the Kuiper Belt scientifically valuable. The inner solar system has been processed and reprocessed 1,000 times over. The rocky planets melted and solidified and were battered by impacts and reshaped by tectonics and coated in atmospheres and stripped of them. The record of the solar system's beginning is largely overridden there, but in the cold of the outer belt, far from the heat that drives change and the collisions that scramble composition, the material that built the solar system has remained almost as it was. The surface of a cold classical Kuiper Belt object is, in a meaningful sense, a sample of the disk that existed before the planets formed, reddish and ancient and patient, waiting in the dark in the same orbit it settled into billions of years ago. One of the things the Kuiper Belt does, slowly and on timescales that dwarf human history, is supply the inner solar system with comets. Short-period comets, the ones with orbital periods of less than 200 years, are not permanent residents of the inner solar system. Their surfaces are volatile. Each pass near the sun erodes them a little, boiling off ice and dust in the bright streaming tails that make them visible. A comet that passes near the sun every few decades will, over millions of years, lose most of its mass. The short-period comets now visible from Earth cannot have been making those repeated passes for the age of the solar system. They would be gone by now. They are recent arrivals, and their origin is the outer solar system. The mechanism is not dramatic. It begins with a Kuiper Belt object in a stable orbit, circling quietly at 30 or 40 or 50 times the Earth's distance from the Sun. Then, across a very long time, Neptune's gravity, not in a single close approach, but in the gradual cumulative effect of thousands of small tugs over millions of years, shifts the object's orbit just slightly. Its path becomes a little more elliptical. Its closest point to the Sun drifts inward a little more. Eventually, it crosses Neptune's orbital path, and at that point, the full range of Neptune's gravitational influence comes into play. The object might be flung outward into a wide looping orbit that brings it back into the inner solar system on a long, slow arc. Or it might be nudged gradually, pass by pass, into an orbit that crosses the paths of the inner planets. In either case, what began as a quiet, frozen body drifting in the outer belt ends, after millions of years and many gravitational nudges, as a comet brightening in the sky over Earth, its ancient ices finally meeting the warmth they were denied for nearly all of their existence. The comet's brief brightness, the tail of sublimating gas and dust catching sunlight as it sweeps toward perihelion, is the visible end of a story that began in silence and stillness billions of years ago in the far outer disk. Nothing about the process is purposeful. The Kuiper Belt object had no destination. Neptune had no intention. The gravitational tugs accumulated as they accumulated. The orbit shifted as orbits shift, and what came next followed from what preceded it, step by slow step, across time that is difficult to hold in a single thought. At the outer edge of the classical belt, roughly 50 astronomical units from the Sun, the population of known objects thins and then drops off sharply. This edge, sometimes called the Kuiper Cliff for the steepness of the fall-off in detected objects at that distance, is not fully understood. The primordial disk should, in most models of solar system formation, extend farther than 50 AU. That it appears to end there is either a genuine feature of how the outer disk was shaped, perhaps by the passing of another star in the early solar system's stellar nursery, or a limit of current survey technology. What lies beyond 50 AU, in the space between the classical belt and the more distant scattered disk and the hypothetical inner Oort cloud, is one of the quiet, open questions of outer solar system science. The answer, whatever it is, will require more time, better instruments, and the patient willingness to survey a part of the sky that offers its secrets only very slowly. The scattered disk begins where the classical belt thins. Its objects are different. Their orbits are larger, more elongated, their inclination steeper, their distance from the sun more variable. A scattered disk object might spend most of its orbit at 30 or 40 AU, then swing out to 100 AU or more at its farthest reach. These objects were not born where they orbit now. They were scattered, flung into wider, more eccentric paths by close encounters with Neptune in the early solar system, when the planets were still settling and the outer disk was still being dynamically sorted. They are the displaced ones, the bodies that came too close to Neptune at the wrong moment in the solar system's youth and found themselves on paths that no longer had anything to do with where they formed. Eris, the world whose discovery in 2005 reopened the question of what the solar system contains and how its members should be named, is a scattered disk object. It orbits the sun on a wide, looping path that carries it from roughly 38 AU at its closest to nearly 100 AU at its farthest reach. At its most distant, the sun is not even a disk in Eris's sky. It is simply the brightest star, a point of light that provides warmth so feeble it barely distinguishes itself from the background cold of space. Eris takes 559 years to complete one orbit. For most of that orbit, it is in the cold dark of the outer solar system, unreachable by any warmth significant enough to stir its frozen surface. And yet Eris is bright. Its surface is coated in methane frost of extraordinary reflectivity, so efficient at returning sunlight that it is among the most reflective bodies in the entire solar system. From Earth, even at its immense distances, it was eventually detectable, a faint, slow-moving point on archival images from Palomar Observatory, discovered in 2005 by a team that had been surveying the outer solar system with methodical patience. When its size was estimated and found to be comparable to Pluto's, the question that the astronomical community had been quietly approaching for years became unavoidable. Pluto had been called a planet for 75 years. Eris appeared to be roughly the same size. If Pluto was a planet, then Eris was a planet. And if Eris was a planet, then so were the dozens of other large objects that surveys were beginning to find in the outer solar system. The solar system's planetary roster would have to grow by an unknowable number, or the definition of planet would have to be reconsidered. What followed was the reclassification, and the reclassification left Pluto as a dwarf planet, the first and best known member of a growing category of bodies, too large to be called minor planets, too embedded in populations of similar objects to be called planets in the full sense. But Eris remained, its orbit remained, its pale, frost-covered surface continued reflecting sunlight with the same calm efficiency it always had. The vote in Prague that gave it a category did not change its path around the sun, did not warm or cool it, did not alter the slow procession of its elliptical orbit through the dark. It was what it had always been. The name was new. The world was old. The survey work continues. Each year, as telescopes improve and the surveys that use them grow wider and more sensitive, new objects appear in the outer solar system. Most are small, too faint for anything but a detection, a preliminary orbit, a catalog number. Some are large enough to warrant follow up observations, to have their size estimated, to be assessed for moonhood, for atmospheric potential, for the faint possibility of future visitation. The work is slow by nature. An object at 40 AU moves across the sky at a rate of roughly 1 arcsecond per hour, a displacement so small that it takes hours of observation, compared against reference images taken days apart, to detect with confidence. For objects farther out, at 60 or 70 AU, the motion is slower still. The outer solar system does not give itself up quickly, but it gives itself up. That is the patient truth of the survey work. Over years and decades, the instruments accumulate data and the analysts accumulate patience, and what was invisible becomes faint, and what was faint becomes known, and what was known becomes a world with an orbit and a size, and eventually, if it is large enough and close enough for sufficient observation, a name and a set of provisional surface properties, and a place in the growing atlas of the outer solar system. The count rises. The map fills in, a little, in the way that all maps of difficult places fill in, not quickly and not completely, but steadily, one faint moving point at a time. What the surveys have consistently confirmed, even as the details of individual objects come into focus, is the sheer scale of the population they are sampling. The classical belt, the resonant populations, the scattered disk, together they constitute a reservoir of material that dwarfs anything in the inner solar system by number, if not by total mass. The total mass of the Kuiper belt is estimated at roughly a few percent of Earth's mass, spread across an enormous volume of space. It is not massive in planetary terms, but it is vast in the sense that matters most to a survey. The number of objects, the range of orbits, the variety of compositions, the accumulated complexity of a region that the solar system has been quietly stalking since before any planet had reached its final size. A wide-field telescope at a high dry observatory site, sweeping the night sky in the direction of the belt's predicted extent, will capture dozens of faint, slowly moving points in a single long exposure, each one a world that had no name an hour before the shutter opened. Most of those points will receive a catalog designation, be observed a few more times to refine their orbits, and then recede into the database, noted, tracked, but not yet studied in any depth. A few of them, the largest and brightest, will earn follow-up time on larger telescopes, will have their sizes estimated by stellar occultation, will be found to have moons, or to be binary objects, or to have surface colors that suggest unusual compositions, and a very few, perhaps one or two per decade, will be large enough and close enough that they will eventually join the small named roster of dwarf planets that the outer solar system has so far disclosed. The pattern across that roster is one of variety. Each large object found in the outer solar system has proven to be different from the ones already known, in ways that were not always predicted. The cold of the outer solar system does not produce uniformity. It produces diversity, different volatile inventories, different histories of radiation processing, different orbital architectures, different interactions with the sun's far-reaching but thin influence. The outer solar system is not a single environment, but a gradient of environments, from the relatively warmer inner belt to the deep cold at 50 AU and beyond, each zone producing its own signature in the surfaces and compositions of the bodies that inhabit it. Against that backdrop of variety, Pluto has always been unusual. It was the first trans-Neptunian object found, and the most observed, and the most visited, the only one so far that a spacecraft has approached closely enough to return detailed images and measurements. But in terms of its orbital family, Pluto is one of many. It is a Plutino, a resonant object, one of the bodies that Neptune captured in its 2 to 3 rhythm during its outward migration. In terms of its dynamics, it is a participant in one of the most stable and well-characterized gravitational patterns the outer solar system contains. And in terms of its physical character, its size, its icy composition, its thin atmosphere of nitrogen and methane, its suite of moons, it sits at the larger end of a size distribution that extends downward through tens of thousands of smaller, colder, less well-characterized objects. What makes Pluto stand apart in human imagination is not its orbital family or its dynamics. It is the fact of its discovery, so long before any of its neighbors were known. For 75 years, it orbited alone in the category of outer solar system objects, the only known world beyond Neptune, and that isolation gave it a singular presence in the planetary inventory. The context that now surrounds it, the belt, the resonances, the other large dwarf planets, the scattered disk, that context was invisible. It accumulated slowly in the data of surveys conducted over decades, and the picture that emerged was one in which Pluto was not an anomaly, but an elder, the first found member of a vast and varied population. That population is still being found. The surveys running now, and the wider and deeper surveys that will follow them in the coming decades, will continue to add to the census. The total number of Kuiper Belt objects larger than 100 kilometers, estimated now at over 100,000, is itself an estimate based on statistical modeling of the detected fraction, the known objects used as a sample to infer the size of the whole. The actual count, if it could be taken directly, would be larger. How much larger is one of the calm, open questions of contemporary planetary science, a question that does not demand an urgent answer, but that accumulates its evidence year by year, survey by survey, one slow-moving point of light at a time. And so the outer solar system continues in its quiet way, the belt spreading around the sun in its great cold flattened ring, the objects within it completing orbits so long that a human lifetime encompasses only a small fraction of even the shortest of them, the resonances holding their precise ratios across billions of years, the surveys adding new members to the census at a pace that will take decades to feel complete, and the whole vast population drifting in a cold and ancient stillness that has outlasted everything the inner solar system has ever done. The light reaching the farthest known Kuiper Belt objects left the sun hours ago. By the time it arrives at their surfaces and reflects back, it carries almost no warmth. It is enough to see by, just barely, enough for a well-positioned telescope to detect the faint smear of brightness that marks a slow-moving world. And in that faint reflection, patient and regular and ancient beyond any useful accounting, the belt continues its long existence, uncatalogued in most of its members, unvisited in almost all of them, doing nothing in particular, going nowhere in a hurry, circling as it has always circled in the cold and the dark and the vast unhurried stillness of the outer solar system, where even light moves slowly through a silence that has no other quality but depth. On the night sky above the Palomar Observatory in California, the air was cold and very still. The telescope dome stood open to a field of stars so densely packed that the eye could not isolate any single point without effort. Among those thousands of fixed lights, on a set of photographic images taken across several nights in 2003, a single dot had moved. It was faint. It moved slowly, the way distant things always move, not with haste but with the patient drift of something very far away, carrying its distance in the quality of its light. The dot had no name yet. It was only a coordinate, a brightness measurement, a position logged against the backdrop of everything that did not move. And then the calculations came back, and the coordinate resolved into something with mass and size and an orbit, and that orbit was enormous, and the world that traveled it was a sphere of ice and rock, sitting at the very edge of what the solar system was known to contain. The astronomers who found it called it Eris, and Eris, without intending to, quietly changed the shape of what the solar system was understood to be. Eris moves slowly through a very long arc. At its closest approach to the Sun, it comes no nearer than about 38 astronomical units, roughly the same distance as Pluto at its nearest. But its orbit reaches outward so far that at its most distant, it sits nearly 97 astronomical units from the Sun. Light from the Sun, traveling at the speed light travels, takes more than 8 minutes to reach the Earth. To reach Eris at its farthest, that same light takes more than 13 hours. The Sun, seen from that distance, is not a disk of warmth and color filling the sky. It is a point. Brilliant, certainly, brighter by far than any other star, but a point nonetheless, a single fierce light in a sky otherwise full of lights, offering almost no warmth. The surface of Eris at that distance falls to temperatures so low that the difference between day and night, between the hemisphere facing that brilliant point and the hemisphere turned away from it, is almost nothing at all. What coats Eris is frost, methane frost, primarily the same volatile molecule that crusts the surface of Pluto and dusts the plains of other icy worlds in the outer solar system, but here deposited so uniformly, so completely, that Eris reflects sunlight with extraordinary efficiency. Most objects in the solar system absorb a great deal of the light that strikes them. Eris returns almost all of it. Its surface is among the most reflective of any solid body in the solar system, a pale, almost white sphere, bright for its size in a way that is almost paradoxical, this far from the Sun, where there is so little light to reflect in the first place. That high reflectivity almost certainly comes from methane and nitrogen ices that refresh themselves slowly, cycling up from the interior or migrating across the surface as the long seasons, each lasting centuries, turn. Eris is a sphere approximately 2,326 kilometers across, that is only marginally smaller than Pluto, and for some years after its discovery, the measurements were uncertain enough that Eris appeared possibly larger. It was this uncertainty, the sense that the solar system might contain not one Pluto-sized world beyond Neptune, but several, that pressed astronomers to decide what exactly they meant when they said the word planet. The decision they reached, voted on in a meeting hall in 2006, classified Eris as a dwarf planet. The same vote redrew Pluto's category, but for the worlds themselves, nothing changed. Dengrev. It will not reach its next perihelion for roughly another 500 years. In the meantime, it moves, slowly and without hurry, through regions of space so cold and so remote that its surface chemistry barely changes from decade to decade, century to century. The frost remains, the pale sphere drifts. Its single known moon, a body large enough to be a small world in its own right, orbits it at a distance measured in tens of thousands of kilometers. And out there, more than 13 light hours from the warmth of the Sun, the two of them travel together through the dark, their shared gravity the steadiest thing in a very quiet neighborhood. Not all of the outer solar system's strange worlds are quiet, still, and slow. Some move in ways that the eye, if it could watch long enough, would find almost violent. Haumea is one of these. It is an icy world, roughly as wide from edge to edge as its companion dwarf planets, but its shape bears no resemblance to theirs. Where Eris and Pluto are close to round, pulled into spherical form by their own gravity, Haumea has been spun into something that looks less like a planet and more like an egg pressed between two palms. It rotates once every 9 hours, faster than almost any other large body in the solar system. At that rotational speed, the centrifugal effect at its equator is large enough to push material outward, distorting the world into a triaxial ellipsoid, longest through its equator, compressed at the poles, stretched so thoroughly by its own spin that its longest dimension is almost twice its shortest. Seen from above one of its poles, it would look something like a flattened oval. Seen from the side, it would look nothing like a planet at all. The cause of Haumea's extraordinary spin is not fully understood. The best current picture involves a collision early in the solar system's history, a large impact that stripped material from what was once a more ordinary spherical body, left the remnants spinning rapidly, and scattered debris into the surrounding space. Two of that debris became moons, Huica and Namaka, both orbiting Haumea in the same plane, both composed primarily of water ice, their orbits carrying them around the spinning, distorted world below, in patterns that interact with each other in complex gravitational dances. The collision picture is supported by a family of Kuiper belt objects that share Haumea's orbital characteristics and composition, spread across a region of the belt as if flung from a common source by exactly the kind of impact that would explain everything else about the system. Dulmet, its moons, and this surrounding family of smaller icy bodies may all be the scattered remnants of one ancient event. And then, in 2017, a stellar occultation, the passage of Haumea's body across a background star, watched by observatories across different parts of the Earth, simultaneously, revealed something that added one more layer of strangeness to an already strange world. Haumea has a ring, a thin structure of material tracing a circle around its midsection at a distance of approximately 2,287 kilometers from the center of the world. A ring around a spinning, elongated, icy body in the outer solar system, confirmed from the way a star's light dimmed briefly, then brightened, then dimmed again, as first the ring and then the world passed across it. The ring was thin. The ring was not like the grand structures around Saturn, broad and layered and bright. It was a narrow loop, faint and spare, but it was there. Haumea became the first trans-Neptunian object confirmed to carry a ring around it, and in doing so it joined a small and growing list of worlds in the outer solar system that are more structured, more varied, and more complex than the simple frozen spheres they were once imagined to be. Making orbits the Sun in roughly 310 years. It is reddish in color, its surface a mixture of methane, ethane, and nitrogen ices, processed by billions of years of ultraviolet radiation and cosmic rays into darker, more complex organic compounds, the same family of molecules called tholins that tint the plains and poles of other icy worlds in varying shades from pale yellow to deep reddish brown. In composition, Making resembles Pluto closely enough that the two worlds are sometimes discussed together. Both are icy, both carry volatile compounds on their surfaces. Both are small enough to fit comfortably within the span of a continent, large enough for gravity to have shaped them into spheres. But in 2011, astronomers watched Make pass in front of a distant star, the star's light carrying information about what lay between it and the telescopes on Earth. What they found, or rather, what they did not find, changed the picture of what a world like Makemake might be. The star's light did not blur or dim gradually as Makemake's edge passed across it. It cut off sharply and completely, and then returned with equal sharpness. On Pluto, a similar occultation would show a gradual dimming, because Pluto has an atmosphere. Thin, yes, but real, with gases that refract and absorb starlight at the edges, softening the transition. On Make there was no softening. The transition was knife-edged. The implication was clear. Make has essentially no global atmosphere to speak of, despite its icy surface and its similarity in composition to a world that does. Why one icy body in the outer solar system maintains a tenuous but real envelope of gas, while another, apparently similar world does not, is a question that the observation raised without yet settling. The precise conditions that allow a volatile atmosphere to persist, and those that do not, depend on factors: internal heat, surface area, albedo, orbital history, that are still being worked out. Make stands as a data point in that ongoing process, a world that does not behave the way its surface composition alone would predict. Beyond the reaches where the Kuiper Belt's population is densest, there is a region with no clean boundary, a place where the outer solar system thins into something harder to define. In this region, a world called Sedna follows an orbit so elongated, so extreme, that it belongs to a different category of strangeness than any of the worlds closer in. Sedna's perihelion, the nearest point in its orbit to the Sun, sits at approximately 76 astronomical units. That alone is remarkable. Most Kuiper Belt objects, even those with eccentric orbits, make their closest approach within 50 astronomical units. Neptune's gravity, which shapes and stirs the inner Kuiper Belt, acts across distances of 30 to 50 astronomical units with real force. At 76 astronomical units, Neptune's gravitational reach is essentially negligible. No known planet can account for Sedna's current orbit. Sedna's full orbit is so large that completing one circuit of the Sun takes approximately 11,400 years. Right now, in the context of the whole solar system's history, Sedna is near its perihelion, as close to the Sun as it gets, which is still nearly 3 times farther than most of the Kuiper Belt. In roughly 200 years, it will begin the long retreat back toward the outer reaches of its orbit, pulling away to distances so vast that for most of its journey, it is simply gone from any practical observational reach. The surface receives almost no warmth, even at this, its nearest approach. The temperature barely distinguishes between perihelion and the cold depths of the aphelion passage. The Sun is a bright point in the sky, and that is all. How Sedna came to be on this orbit is one of the outer solar system's open questions. A close encounter with another star during the early period, when the Sun was still embedded in its birth cluster, a dense group of young stars that have long since dispersed, could have nudged a body from a more ordinary orbit into the elongated arc Sedna now follows. The influence of an undiscovered massive body in the far outer solar system is another possibility that some researchers take seriously, though no such body has been directly confirmed. Both pictures are hypotheses, not settled conclusions. What is known is that Sedna is there, that its orbit requires an explanation that current models of the solar system's history do not fully provide, and that its discovery was a reminder that the outer reaches of the solar system hold configurations of matter and motion that no one had predicted. The cold out there is not empty. It is populated by worlds in all their variety, some round and some irregular, some paired with moons and some solitary, some faintly visible and some all but beyond the range of any telescope currently built. Each of them carries something, a surface texture, a color, a shape, a density that reflects the particular history of its formation and the particular nature of the collision or migration or chemical process that made it what it is. No two are identical. The outer solar system is not uniform, it is a collection. Quaoar was identified in 2002, a world orbiting at a distance of roughly 43 astronomical units, fitting more comfortably within the classical Kuiper belt. Its orbit relatively circular, its size placing it among the larger trans-Neptunian objects, roughly 1,110 kilometers across, large enough for gravity to have shaped it into something close to round, though not so large as Eris or Pluto. Quaoar, when it was found, seemed like a straightforward member of the belt. Icy, cold, reddish, equipped with a small moon, Waywatt, orbiting it at a modest distance, a world among many. Then in 2023, observations confirmed that Quaoar has a ring of material orbiting it at a distance well outside what models of ring formation had predicted to be the stable outer boundary. Within a certain distance of any world, a boundary calculated from the world's mass and its density, tidal forces are strong enough to prevent orbiting material from clumping together into larger bodies. This is the Roche limit. Within it, rings can persist because any tendency of the material to gather into clumps is continuously overcome by the gradient in gravitational pull across the clump's width. Beyond the Roche limit, the models say material should coalesce rather than remain as a ring. Quaoar's ring sits well beyond its calculated Roche limit. It should, by the existing framework, have gathered itself into a moon by now. It has not. The ring persists. The reasons are not yet understood with confidence. The density and composition of the ring material, the orbital dynamics specific to Quaoar's particular rotation and mass distribution, the possibility that the ring is young and simply has not yet had time to coalesce. These are ideas under consideration, not settled answers. Quaoar's ring is a structure that current understanding cannot yet fully account for. There is something very calm about that, not unsettling, but genuinely open. A ring curves through space, around a world most people have never heard of, in a part of the solar system no spacecraft has visited, and the physics that would explain it precisely is still being written. The outer solar system is not a problem solved and shelved. It is a record being read, slowly, across years of careful observation, each new reading adding one more detail to a picture that has been changing continuously since the first faint dot moved across a glass photographic plate and revealed that the solar system did not end at Neptune. What all of these worlds share is the condition of distance. They move through regions where the light is faint, where warmth is almost non-existent, where a year measured in human terms stretches into centuries or millennia. Eris will not return to its current position for roughly 559 years. Sedna takes more than 11,000 years to complete one orbit. On these timescales, the history of human civilization fits inside a single orbital period. The fall of every ancient city, the building of every monument, the written record of every language now spoken or now lost, all of it fits within the span of one Sedna orbit. And Sedna moves through that time the way it always moves, without accelerating, without pausing, carrying its surface of ices across the cold arc of its path, in the same way it has for billions of years. The ice on these worlds is not simple. It is layered and altered, built up slowly from volatile compounds that freeze onto the surface during long cold periods and sublime, passing from solid to gas during the warmer stretches. Methane, nitrogen, carbon monoxide, water in its rigid crystalline form. These are the building materials of the outer solar system's surfaces. Over billions of years, the ultraviolet radiation streaming outward from the sun diluted these distances, but still arriving, still acting, and the high energy particles of the cosmic ray background work on those ice molecules, breaking them apart and knitting them into longer chains of carbon and hydrogen and nitrogen. The products of this chemistry are dark. They are reddish or brownish, complex in composition, and they accumulate on surfaces over geological time until the red-brown tint is the dominant color of an untouched icy world. The tholins, a loose term for this family of radiation-processed organic compounds, are not alive. They carry no biological information, but they are complex molecules built from simple ones by the steady work of radiation and time, and they are present across almost every icy surface in the outer solar system in some amount, a common thread connecting worlds that are otherwise quite different from each other. The surfaces of these worlds hold their chemistry in a kind of suspended record. Unlike the inner planets, where volcanism and erosion and plate tectonics continuously resurface the ground, erasing what came before, the outer solar system's worlds are mostly geologically quiet. What is on the surface has often been there for a very long time. The reddish tholins on Makemake's surface accumulated over billions of years. The methane frost on Eris may be refreshing itself on timescales of millions of years, but the underlying rock and older ice beneath it are ancient. The water ice that forms the bedrock of most of these worlds condensed from the solar nebula in the earliest centuries of the solar system's existence. When the instruments of a telescope measure the spectral signature of a surface compound on one of these distant bodies, what they are reading is a chemistry that was set in motion more than 4 billion years ago and has been running, slowly and without interruption, ever since. Some of these worlds have moons. Eris has its companion Dysnomia, orbiting at a distance that allows astronomers to calculate the system's total mass. Haumea has two, tumbling in their orbits above the spinning, elongated body below them. Quaoar has Waywatt. Most of the larger trans-Neptunian objects appear to have at least one companion, and the pattern suggests that collisions in the early solar system, when the disk of material was denser, and encounters between growing bodies were more frequent, commonly produced gravitationally bound pairs. The presence of a moon is both a physical consequence of the violent history of the early outer solar system and a practical tool. The orbital period and distance of a moon around its primary can be used to calculate the primary's mass with a precision that direct observations of the world alone cannot achieve. The moons of these distant worlds are small and faint. They were not suspected before the era of large ground-based telescopes, and later the instruments carried to orbit above Earth's atmosphere, which removed the blurring effect of the air and allowed smaller, fainter, closer companions to be resolved. They are not dramatic features. They do not fill the sky above their primary worlds. They are mostly small icy bodies circling larger icy bodies in the cold, their orbits stable, their surfaces reflecting what little sunlight reaches them in almost perfect silence. The relationship between a distant dwarf planet and its moon, the slow gravitational bond, the steady orbital rhythm maintained over geological time, is one of the quieter truths of the outer solar system, that even at 50 or 70 or 97 astronomical units from the sun, gravity is patient and persistent, and the bonds it builds between bodies are old. The number of worlds in the trans-Neptunian region that are large enough to be spherical, large enough to have been shaped by their own gravity into something smooth and round, is not fully known. Current estimates suggest there may be dozens, perhaps more. The surveys that have been conducted have covered large portions of the sky, but the objects are faint, they move slowly, and distinguishing a large distant world from a smaller, closer one requires observations taken across time, watching for the drift that reveals an object to be local rather than stellar. Many candidate worlds have been identified as bright, slow-moving points in survey data without the follow-up observations needed to fully characterize their orbits and sizes. The outer solar system is not empty of large worlds. It simply keeps them at distances where finding them takes time and patience and clear skies and careful arithmetic. The surveys go on. Each new wide-field telescope that comes into operation, each new survey of the night sky, conducted across months and years, adds to the census. New objects are found, designated, given preliminary orbital parameters, then slowly confirmed and refined. Some turn out to be smaller than initially thought. Some turn out to be larger. Some have companions that were not suspected until a second look. The picture of the trans-Neptunian population is not a fixed thing, not a completed catalog. It is an accumulating one, added to year by year, each addition requiring a small adjustment to the overall model of how the outer solar system formed and what it contains. What is clear is that the region beyond Neptune is not a void punctuated by a few lonely oddities. It is a populated place in the way that a very cold and very dark and very large landscape can be populated, not densely, not obviously, but genuinely and extensively. The bodies there were built in the same collapse of gas and dust that built the inner planets and the sun, formed from the same disk of material, shaped by the same gravitational processes, and set moving in orbits they have maintained ever since. They are not visitors or interlopers. They are original members of the solar system, formed in the earliest period of its existence, some of them barely altered since. Their surfaces are archives, their orbits are records. Their compositions reflect the temperature and chemistry of the solar nebula at the distances where they condensed. Eris drifts on its long arc, the methane frost on its surface, unchanged across centuries, the sun a bright point above it that provides just enough radiation to hold the frost at a particular equilibrium. The small world Dysnomia circles it, taking just under 16 Earth days to complete each orbit, and that period does not change, has not changed, will not change until something external arrives to disturb it, and nothing is near enough to do so. Haumea spins in its elongated form, the polar regions compressed, the equator bulging, its ring tracing its narrow circle in the cold, the two moons above it making their own careful circuits. Make moves through the belt at a distance and speed it has maintained for billions of years, its surface unbreathed upon, its chemistry accumulating the slow dark products of radiation and time, its occultation shadow continuing to pass, once every orbital period, across whatever background stars happen to be, in the right position in the sky. Sedna moves outward now, beginning the long recession toward the aphelion that will carry it so far from the sun that it will be nearly invisible to any technology on Earth, and it will remain there, drifting slowly at its far point for thousands of years before it begins the return. Quell's ring curves through the space around it, the particles of ice and material that make it up circling in their own small orbits, each particle following the path that gravity and the dynamics of the system determine for it, the collective motion sustaining the ring's form, despite the conditions that suggest it should have gathered into something else by now. The ring does not know it is outside the boundary where it should be able to persist. It simply continues. the particles continue. The orbit of each grain of material continues, uninterrupted, indifferent to the models built to describe it. There is a quality that all of these worlds share, beyond their icy compositions and their great distances and their slow orbits. It is the quality of duration. They have been doing what they are doing for an enormously long time. The outer solar system is not a young place. It is one of the oldest, in the sense that its constituent bodies were among the first to form, and many of them have experienced the least alteration since. The processes that are changing them, the slow accumulation of tholins, the occasional resurfacing by volatile ices, the gradual transfer of material between Pluto and Charon's polar cap, operate on timescales that make geological time on Earth look brisk. A mountain range on Earth can be built and eroded within 100 million years. The chemistry on Make's surface has been running for 40 times that long. That duration produces a kind of stillness. Not the stillness of nothing happening, but the stillness of processes so slow they look like rest. The ices hold. The ring persists. The orbit continues. The frost refreshes itself imperceptibly across millions of years. The two moons of Haumea circle their spinning, elongated host, and the distances between them stay constant to within the width of a small number, maintained by gravity acting moment to moment in the cold. At no individual moment is any of this dramatic. It is simply continuing, world after world, orbit after orbit. The outer solar system's population moves through the dark in the same paths it has followed since the solar system was young, carrying the chemistry and the texture and the orbital mechanics of 4 billion years, wearing that history lightly, in the patient way that only very old and very cold things can. The sun's light takes a long time to reach these worlds. It arrives diminished, almost more conceptual than warm, a direction in space rather than a source of heat, a bearing rather than a comfort. And yet it does arrive. Even at 97 astronomical units, even at the far stretch of Eris's orbit, a photon that left the sun this morning will reach that pale frosted surface before the day is out. There is a thread, however attenuated, connecting the warmth at the center of the solar system to the cold at its edge. The same star that illuminates Earth's blue oceans and warms the soil where seeds germinate also sends its light, faint and patient, to touch the methane frost on Eris and to fall, unnoticed, on the ring around Quaoar and on the slowly tumbling moons of Haumea and on the smooth, airless, ancient surface of Make. All of it connected, all of it part of one system that formed together from one cloud, that has been moving together ever since in the slow gravitational agreement of bodies bound to the same center. The outer solar system is not a place that ends. It has no clear outer wall, no moment at which space becomes something different. The Kuiper Belt's population thins with distance, and then thins further, and then the individual objects become rare enough that the spaces between them are larger than the inner solar system entire. Beyond that, the scattered disk carries its more eccentric members on their longer, wilder paths. And beyond that, the Oort cloud, if it exists in the form the models describe, holds a reservoir of icy bodies in orbits so large that they barely qualify as solar at all, bound to the sun by gravity so gentle that a passing star can sever the connection and send a body adrift. But these distant structures do not mark an end. They are continuations, each one further, each one slower, each one colder. The solar system dissolves rather than stops. It becomes gradually less itself, and gradually more simply space, not with a boundary, but with a slow diminishing. The worlds in the cold middle of that dissolution, the ones with names, the ones that have been found and measured, and whose surfaces have been red in the light they reflect, carry something that belongs to the very beginning,